Third floor.
Hello.
और चलछुं नेट चलछुं देखुं
Hello. Good morning. distinguished speakers. Professor Ajit Kembhavi, former directors, IUCAA, share their insights on the life, work, and influence of Professor Narlikar and guide us in appreciating the pathways his mission continues to open for the scientific community. To mark the auspicious beginning of this symposium, I now request our esteemed dignitaries to kindly join together in the ceremonial lighting of the lamp. The lighting of the lamp has always symbolized the dispelling of darkness and the spreading of knowledge. A befitting gesture to commence the symposium dedicated to the memory of such a great teacher, communicator, and scientist. Thank you. Moving forward with our inaugural session, may I invite Professor Dash, Head, Department of Physics, Assam University Center, and the event coordinator of this previous symposium to deliver his welcome address and set the tone for today's event.
Good morning to all of you. Esteemed guests present here, Honorable Vice Chancellor in Charge, Professor Ashok Kumar Sen, Dean Physical Sciences, Professor Prof. Chaudhary, our guest, Professor Naresh Dadhich, Professor Ajit Kembhavi, my colleagues, research scholars and dear students. When we heard the news on May 20, Professor Narlikar is no more, immediately myself and Professor Ashok Kumar Sen, my supervisor, were discussing about his for last few decades he was involved in research as well as testimony population program. Then we thought there should be a memorial lecture in our department, and then immediately I contacted Professor Ajit Kembhavi sir for organizing a lecture in our university. And after that, I also contacted Professor Dadhich, and both of them agreed and told me that Himadri, is it possible to organize the program in the month of month of September, August or September? I told yes, it is possible. Anyway, we didn't get enough time to organize this, but anyway, we are organizing this program. as a part of our IUCAA center is there in our department, ICAR. So, okay, and it was organized by our department. Then you can see another poster here. Just after 2 days, 1st to 3rd February, we had a symposium where Professor Naresh Dadhich and Professor Ajit Kembhavi attended that particular symposium. I will also show you in this particular room. 17 years before that symposium was organized. Yesterday night, actually, it took time to find out all these photographs, but thanks we had found out. So you can see this is our foundation stone. It is just at the entrance of our department. You can see Professor K. Kostiranga is here, and you can see our then HOD, Professor Anandu Bhattacharya, he is no more now. Our Honorable Vice Chancellor, Professor Tapati Bhattacharya, and other Professor Narlikar is also here. No, it is not his photograph. He joined later. I'll show you. So here you can see some photographs in our department. So this is the HOD's room. Professor Kostiranga were discussing with us. Now, this is one of the photographs when just after their departure, Professor Narlikar came to our department. We had a discussion with him. Just after their departure, he was sitting there and he discussed with us regarding the astronomy program in our department. He had a cup of tea with some of our colleagues as well as students. I think Professor Indrajit Sharma was also there in that time. I saw in photographs. Next was the National Symposium on Astrophysics, Spectroscopic Data and Photometric Data. Just after 2 days, we organized this symposium, and we could see Professor Naresh Dadhich, Professor Kembhavi, along with Professor Amarjyoti Choudhury, Professor Shurlaja Mukherjee, Professor our Vice Chancellor, Professor Tapati Bhattacharya, Professor Ashok Sen, Professor Anandu Bhattacharya are sitting here. So this is in the same room it was organized. So this is the inaugural song. And Professor Naresh Dadhich, I was discussing this in the morning. Then Professor Kembhavi. So these are the part of it. It was a very rich program that time. Now in 2008, because many students also joined in that symposium. So it is all about the history of this department, because we have a close connection with IUCAA as well as many astronomers of this country, and we are trying to start a new journey. And today it's a day when we will actually talk about Professor Jayant Vishnu Narlikar, his contribution. After this inaugural session, Professor Kembhavi and Professor Dadhich, they are contemporaries and Narlikar, and they will talk more on that. And thank you very much for joining this session. Tomorrow we have public talks at 2:45. We have organized this in the Within Park Conference Hall. So I request all of you to join. Some of our friends and colleagues are online because this is actually telecast, live telecasted in the YouTube channel. So I will also request viewers to be with us tomorrow at 2:45 p.m. Thank you very much.
For your warm words. Now, with due honor and tradition, I would like to invite the dignitaries to kindly take their seats on the dais. May I request our distinguished speakers, Professor Ajit Kembhavi and Professor Naresh Dadhich, to please come forward and grace the dais. I also request Professor Ashok Kumar Sen, Vice Chancellor in charge, Assam University Shilchar, Professor Kauravi Dr. Dean, Albert Einstein School of Physical Sciences, and Professor Himanshu Shekhar, Head Department of Physics, as well as the coordinator of this event, to kindly take their place on the dais. It is now our privilege to extend a warm felicitation to our distinguished speakers as an acknowledgement of their valuable presence in our department during this symposium. May I request Professor Taj to ceremonially welcome Professor Ajit Kembhavi with an Inaugural. I also request Professor Shen to present him with a memento as a token of our respect and gratitude. Thank you, sir. I now once again request Professor Taj to extend a traditional welcome to Professor Naresh Dadhich with the Inaugural. I also invite Professor Ajit Kembhavi to the dais in order to present our speaker with a memento, representing a gesture of our esteem and gratitude. Thank you, ma'am. Thank you, sir. Moving forward with our inaugural session, I request Professor Kauravi Dr. Dean, Albert Einstein School of Physical Sciences, to kindly share her thoughts and address the gathering. Thank you.
Very nice morning. To all of you present over here, our honorable Vice Chancellor is here, Professor Ashok Kumar Sen sir, and Head Department of Physics and convener of this program, my other colleagues from Department of Physics and from other departments, and today's distinguished guests, Professor Dadhich and Professor Kembhavi from Inter-University Center for Astronomy and Astrophysics. My dear research scholars and students and the participants, so, on behalf of Albert Einstein School of Physical Science, I welcome all of you in this program, the 3-day Symposium program. Actually, I know that this is not my assumption. I was sure about that the Department of Physics is one of the vibrant departments in our school, and the photographs justify that my thinking is right. So in today's program, actually what we have decided, that is this, you see that our Boradpuri is the remotest part of the country. We decide the communication is not so good, we can say. So this type of program, when we will take this type of program, like popular talks, seminars, conference, and scientific initiatives, and these such type of programs are the great influence and great opportunities to connect with the global academic community. So through this symposium, I hope that this networking, whatever will be done through this symposium, so this networking, there will be deep discussions, and this discussion will focus on the origin, on the study of the origin and the evolution of the universe. And as a result, this interaction, such interactions can lead to the development of new theories. So it is a great opportunity for us who reside in the remote area. Professor Narlikar, the mission and vision of Professor Narlikar was to popularize science, and he has he tried to achieve his goal by nurturing the inquisitiveness and query of such type of things. And for that, to achieve his goal, he has dedicated his life with tireless effort, and the commitment towards the mankind. And I hope that all this discussion will be held in this 3-day symposium. I have seen the program. There are different talks and different sessions will be taken, will be chaired by the eminent scientists of from different parts of our country, and not only from different parts of our country. Our faculty members from this department will also be involved there. So I hope that there will be a vibrant discussion and vibrant participation, so that we can achieve a new goal, new achievement will be there out of this symposium. So with these thoughts keeping in my mind, I extend my best wishes for the great success of the program. Thank you. Thank you.
Thank you, ma'am, for your encouraging words. Though during the next 3 days, we would hear from our esteemed speakers, but since this is the inaugural session, I would like to invite our esteemed speaker, Professor Ajit Kembhavi, to express his thoughts with us. Sir, please.
Good morning, Vice Chancellor, Dean, and Head of Department, and my friends. I'm already going to impose myself on you for 3 lectures. What will I do tomorrow? So I don't want to take any additional time. It will be really excessive. Let me just say one thing. Is that there are 2 central universities in Assam, one on the Barak here and one on the Gujarat. Tezpur. And I have had the privilege of seeing both these institutes building in sheds. So Tezpur was in Tezpur, it had one single shed, exactly at the time when IUCAA was in one shed. And then it was grown to a magnificent campus, and exactly the same thing had happened here in Silchar. I did not see Silchar University anywhere else. It started with this campus, but I have visited Professor Himadri in his lab, in the shed, and now we have a beautiful department. This morning, my colleague Naresh and I were walking over the campus. It's so beautiful and inspiring. And I'm sure that all of you will do very well there. So we hope to have some interaction with you. Please don't hesitate to come and talk to us if you are around much of the time. If you discuss anything at all, please feel free. Thank you very much.
Thank you, sir. I now request Professor Naresh Dadhich to kindly address the gathering. Sir, please.
Friends, first it was wonderful to see how young people look 17 years back. Very nice for the market to remind us that this step of all of us is step become great. And the white folks were also the same one that we said that both these universities we first visited when they were really starting up. The states around them is all that time to go around. And both these places have come out so very nice. And I think probably I didn't beat this after 2000 years, so 17 years is a long time. I'm very happy to be like that. Now, we are getting here to expound on the legacy of the great man, Professor Narlikar. Now, you see, if somebody is great, then it's easier to say to pick up. But there is somebody who is an all-round great. There was whatever you would have asked for an intellectual, he did it. And he did it wonderfully well. Each one of them, whether it's science, whether it's issue building, and that is our thing, because we, two of us are very fortunate to be part of the building of the institute which is started. And that the science communication, science popularization, writing books for all the three languages, English, Marathi, mother tongue. And actually, his mother tongue is he grew up in Banaras. So in all these things, and above all, he was a great human being. And I think I must tell you that since we were involved in working together in this, building the institute, one thing which struck you was he got the best out of it. He knew what is your strength, and he involved you. And other thing was, even when they tell you very small little thing, he has a knack of involving you. So I think in the initial stages only three of us were there. Even if there is some simple decision that to be taken, which you could have done, there is nothing. But no, if you are around, you call us. And that's it. Should we do this? Now, in that let's say that if you are here as such a formidable group with everybody who interacted with it was really really very admirable, great admiration and great respect. And more being anywhere. Thank you.
Thank you, sir. Now it is my privilege to request our Vice Chancellor in charge, Professor Ashok Kumar Singh, to express his thoughts with our gathering.
Yeah, good morning everybody. I am here on behalf of our regular Vice Chancellor, Professor Ajit Kembhavi. I welcome our distinguished guests, Professor Naresh Dadhich and Ajit Kembhavi from IUCAA Pune. In this occasion where we remember go through the reminiscences, whatever we had association with Professor Jayant Vishnu Narlikar. Professor Narlikar came to Assam University in 1999. He actually came to GC College, and this university campus was just being built up. We had our Assam houses, sheds. So one day he spent here. The founder DC was here, and he gave it talk here. That time, I think he was Prime Minister's science advisor also. So a lot of security were raised in the campus. So this is an occasion where we can remember whatever we had came from Professor Narlikar's presence in Assam University, especially learned from him. As an individual, I had also some association with Professor Narlikar. I was one among the first batch of postdocs. I stayed with Professor Narlikar for 3 years. And actually, Professor Naresh Dadhich and Professor Ajit Kembhavi, they are my senior colleagues with whom I have worked at IUCAA, different scientific activities, science popularity program. And I welcome both of you, sir. I thank our Dean, Madam Professor Dr. Chaudhary, for her kind presence and patronage. And of course, Professor Himanshu Sekar, who is my PhD student and now actually. So we were planning about this. Even I had discussed with our DC, Professor Ajit Kembhavi, about this program. He was also looking forward to, but he had to suddenly leave for Rajasthan for some official work. So once again, I welcome all of you here on the dais.
Thank you, sir. To formally bring the inaugural session to a close, I now request Professor Ajit Kembhavi to propose the vote of thanks. Thank you.
Very good morning to everyone present here. The respected Vice Chancellor in charge, Professor Shen, Professor Dadhich, Professor Kembhavi, Dean Madam, Professor Dr. Chaudhary and HOD, all the participants here. So at the outset, I would like to thank the experts actually who are coming from such a long distance for this event, which we have planned to organize in memory of Professor Narlikar. As you have already seen that Professor Narlikar visited this department, actually he spoke in this room. So we have a fond memory of him. So So we tried to introduce you to his legacy, which is, as Professor Dadhich has already told, that it's a multi-faceted thing. So that is what we look for now in science community. I thank Madam Dr. Chandri for supporting us in our venture, to all the administrative support we received to organize this event, also to the participants without whom we could not have a program, everyone who is associated in organizing this, our scholars, our food suppliers, they are very important. This system, everybody who have associated with this program, I cannot remember everybody's name and it's not possible in this short span to talk about everybody. But it's a collective effort and we would like to thank everyone with gratitude on behalf of the department. I thank you all. Thank you.
Thank you, ma'am.
The inaugural program is over formally. I just want to say a few things as a teacher from this department. We have many students, I mean all of you who are sitting here, many of you are research scholars and some of you are PG students in your third semester having astrophysics as special paper. Professor Naresh was director of IUCAA. So, Professor Ajit Kembhavi, former director. Professor Naresh works on general theory of relativity and all related things in our department. I can see some of the research scholars who are working in general theory of relativity. You please contact him, discuss him, whatever doubts you have in your mind. Sometimes you ask me, I refer his work. So please discuss with him, and also Pakistan has many students working in dark matter, dark energy, some cosmological models. When such research scholars are there, please discuss with Naresh. Also Professor Ajit Kembhavi, who is an expert in data science, big data, then data mining for all the web-based telescopes, image processing. He also works in extragalactic astronomy. So this is a wonderful opportunity for all of you. They are available here. So, I mean, they are very friendly, don't feel scared of them.
Thank you, sir, for conveying this message to our participants. Now, our inaugural session comes to an end, and we will break for tea, which will be for 5 minutes. And after that, we will gather here once again for the talk, Jayant Vishnu Narlikar, his Life and Science, delivered by Professor Ajit Kembhavi, followed by Professor Naresh Dadhich. So, meet you again in 5 minutes. Thank you. his life and science. Delivered by Professor Ajit Kembhavi, former Director, IUCAA. I request Professor Kembhavi to kindly take over the stand.
Yeah. So you can just come in front, like you feel or the front is ready. Please go for it. Aspect you can keep better, but less the rest you feel left. Sanjay, you already? If already, just close the door. Sanjay, let us start. You start, Sanjay. Please.
So good morning. Can you hear me properly? Can you hear me? Yeah. So I'm very glad to be here with your talk on Professor Jayant Narlikar. And I made it very informal. I'll show you a lot of pictures and slides. So there is his life and that's what he did. And then I'll also talk a little bit about his science. But if you need to ask any questions later, you can do that in case you can see in afternoon or tomorrow. So I worked with him. Okay. So I worked with him for a very long time. I was one of his PhD students and then he offered me a job in IUCAA and then we worked there together. And then we moved to Pune to start IUCAA. And in all, I worked with this for just short of 3 years, which is a very long time. So my talk is based on my personal experiences. And he was, so you would have been used for a couple of months, you have been 87 years old. And you are my collective factor. And here you see, he was a very famous person, so there are a lot of cartoons of him. But this one particularly drawn, just somebody who was a very fine cartoonist in Tehran, the newspaper from Bangalore, and he requested him to draw this as a presentation to him when IUCAA was inaugurated. But I don't know how many of you have actually seen him or not. He was a very soft and gentle person. And he was clearly always smiling. And he very rarely lost his temper or got annoyed about anything. You can see here that he was always angry. I'll tell you later what it was about. Then, I'll go to that. So he was born in a city called Kolhapur in Maharashtra. But at that time, his father, Professor Vishnu Narlikar, was one of the earliest general lecturers in the country. And he had gone to Cambridge and studied. He was a writer himself. And then at one time I believe that there were only two students doing business activity in the country. One was Professor Vishnu Narlikar and the other was NTSA. When really everybody was in India was a student. And of course, Professor Senior Narlikar moved to a student. was P.C. Vaidya. This was his first school. And P.C. Vaidya at the time was located in Banaras. And he has told me himself about how that work went. And if you look at the gravitational field of the star radiating, because Einstein's equations are extremely difficult to solve. And a very good, very useful solution, like a short-term solution. And this is like a short-term solution with the radiation which is going out. And that is called as the vitametric solution. So he was the first student of Vishnu Narlikar, and Naresh Dadhich, who is sitting here, was the second last student, but that was in Pune University. So that you can see here, and early here, and he was Narlikar was a very systematic person. He always wrote very beautifully, both on the bone and on the paper. And he can see here that he completed the binomial scale because the bananas are very, very deep. And you can see you actually see the date here, 1971. So I'll again come back to this photograph later. So at that time, he was 20 years old. And that is more or less the time that all of us studied the binomial scale. And so this is the time when he left for Cambridge. After he finished his PhD in Banaras, can you do whatever you want to do, but please don't distract me. Okay, because I'm thinking that I'm talking to you, keep dancing around, I love those stuff. Please don't distract me. It doesn't matter if the fan is off, fan is off. Okay? So there was a time when he did his PhD in Banaras and then he went to the University of Cambridge for his PhD. You can see here, at the time that he was living, his father and his mother, Srimati Narlikar. The father was the electrical engineer, the mother was a Sanskrit scholar. So I had the privilege of knowing both of them, and she used to teach Sanskrit slokas to my son when he was very young. And she was herself a very learned person. So it was an extremely educated household. And she came from a family which is known as the Usul Mathematics. Okay, they are from Pune. And they were mathematicians and statisticians. So we see that for 2 generations, science, mathematics, etc. was part of everyday family activity. And so then, when he reached Cambridge, he again did a tripods. The tripods is a bachelor's degree that is equivalent of a master's. So he did a tripods, and one of the very famous colleges in Cambridge. So because you have the University of Cambridge, it is like this. It's a centralized university, and they don't have all the campuses, but it has got a lot of colleges. And these colleges are unlike our colleges, they are not teaching based. So somebody will take a PhD or a BSc or whatever, you join a college, and they will be tutors there for the college, and they live in the college, using the college, so they will always have this lecture in the university. And these colleges like Cambridge and Oxford, as you know, are extremely famous. The best people in the world used to go there. And all sorts of leaders of British it's very great to visit these colleges and be there. And for example, in Trinity College, you can see the similar room in which Newton used to be there. So everything is several hundred years old. It's very exciting. Then, so you can see here, there is a very beautiful king state. And there is a river camp. And the river camp is not like the Brahmaputra or the Bara. It's just a small thing like in Nana. But it's very famous, and you can do hunting there. There are the rafts on this. There is one village called Manchester. And Manchester, they will have something called a king. And Manchester is a very famous city, including what you know, John Keats was a poet, Bertrand Russell was a philosopher and mathematician, and then there are also Jeffrey Archer, some of you have read his books. So So I'm telling you this because it's a very beautiful and serene place. It's full of education. And it's not that it's all the scientists and the best teachers in the world. It's just that there's somebody like Iraq who gives you a lecture on the leg, who can affect you very deeply. Right? So, and then since the best students come, then contemporaries will also. So we see that when you are interacting with each other, when you are in a university like this, you are dependent on your teacher to teach you. But even more importantly, you learn from your contemporaries, you learn from your friends and you talk to each other. Which is a very big parts of it. When you see this here in the photographs. So this is the Narlikar which you are doing this. And there are other very famous associations which are for SM Chitre. And he would learn to watch it. And he was very famous for his work on neutron stars and generally oscillating stars and so on. He died 2 years ago. They both went together to Cambridge on the same boat. But there is not much difference before that. So they got introduced and then they became lifelong friends. So I have actually done that. And here you can see Narlikar with his mentor and guide, Fred Hoyle. You must have heard about Fred Hoyle. So he was a very great astrophysicist. And he was, if you take any big idea in astrophysics now, you see that Fred Hoyle has made a contribution. So he worked in two different ways. In one way, he was working in classical astrophysics and the main line, and the development of astrophysics was very heavily dependent on the ideas. But at the same time, he also had many iconoclastic ideas, which are very unconventional ideas. And he came out with those and put them out for discussion, and they do very bitter fights and rivalries for the science. But that also led to a lot of creativity. So Fred Hoyle was a truly remarkable person. And so here you can see the graduation photograph of Professor Narlikar and his colleagues at Cambridge Different Department of Care. And this is his brother, Ajit Narlikar, who is also a physicist. So this is Professor Jayant and his wife Mandala, who had student after they got married. And she was a mathematician in her own time. Okay, so she used to work with KR for Mumbai. She was a very well-known mathematician. But later on in her life, what she did was that she dedicated herself mainly to teaching. And the teaching also to the underprivileged. So she used to go to small colleges and people there. It was also a remarkably helpful person. So when I was educated, she was a very tough person. She was not a very good person. But she was remarkably helpful. And she used to do, she would treat us all as a very young children. And she used to make things for the cakes for us. So, and whenever we had a birthday, she would always send a cake. Right up to last year when she died, she had gone through cancer for many years. And the interesting thing was that on my most recent birthday, my daughter met the same people. And without a year, they have 3 daughters. So, the eldest is Geeta. She's an extremely well-known biologist. She's in the US. And then the middle daughter, Elisa, who is a very well-known computer scientist. She worked for Google, again in the US. And the youngest daughter is Lila, who is a computational biologist. And she is a professor in IUCAA. So the tradition continues with that. So now, so there are 3 phases in my talk. The first phase was his early thinking and how he went to. Now I'm going to talk for a short time on his research in Cambridge, which was quite remarkable and very, very famous. And then after that I'll talk a little bit about IUCAA. And whatever I say and don't say, Naresh will have to take his part of it. So you should take the talk together. So he started his work in 1960. Then he left Cambridge in 1972. So that's a very great deal of work to do. So the first problem we worked on was the distribution of cosmic sources. And this was more or less an accident. And then galaxy formation. How are galaxies formed? This very same theory. Marx time selected and I don't have time to go into the extent of the examination, but it's very, it's a very fascinating subject that first done by Iran. So I can tell you very quickly what it is about. So if I got an electron which is accelerated to negative radiation, that's all of you have studied. Any charge particle is accelerated in this radiation. Now this radiation travels forward in time. Right, so therefore, if an electron is accelerated in phase 2, it will take a fraction of a second for that to be released. Right, so it is called retarded. T minus R by C. So you are completely comparing. But every T minus R by C solution also the T plus R by C solution. So it will make backwards. So the question is, why don't we see signal going backwards? And Iran worked on that. There is a remarkable paper, and after that they worked on that. They worked on it, and it happened because of cosmological considerations. Okay, but maybe someday I'll come back to Switzerland and talk about that. People interested. Okay, then the problem is to make the variable calculation and so on. So now let us see what are the things and this is the see this picture. Rubber deep. So this is taken the picture of a small part of the star. Very small part of the star. About a couple of arc meters. You know what is arc? 60 arc meters is 1 meter. So 2 arc meters or 2 arc meters. So you can see this here. And this is an extreme deep field. Deep field meaning you can look at one part of the sky, only part of the sky, and you observe it for a very long time. So you can see, and then when you observe it for a very long time, you can see galaxies which are very far. There is nothing which is a star. Every dot that you see, number of phase, is actually a galaxy. Every galaxy has got different stars. Right, so and then we know that each galaxy has got each star and got many planets and exoplanets. So you are talking of 10 to 11 planets. It is a very immensely large universe. The only way in which you can study is to make a very simplified assumption. So the assumption that you make is one of the cosmological reasons. And it tells you that the universe is homogeneous. You can meaning whether you look at it from how much information, or if you go to a galaxy which is very far away, you will still find the universe to sustain. Number one. Number two is isotropic, meaning that in whichever direction you look at the universe, you will find that it is the same. So you will say, how is that possible? Because if you look at that clearly, what is happening in the direction is different from what is happening in the direction. That is because this is a small particle. Right, so when you take it to the large, then you get isotropic. So these are the basic assumptions of cosmology. And then the observation first made by Hubble and then the universe is expanding. I'm sure all of you know. The universe is expanding, and the further the galaxy is from us, the faster it is. And that's what Hubble developed now. And because the universe is so large, and because the galaxies are so massive and there is so much matter, you cannot apply different scale of gravity to this idea. Though Narlikar spent a significant amount of time studying European cosmology because of the circadian cycle, so you need to understand central. So when you do that, you get this picture of the universe. People are not able to back here, and then the idea is that the whole universe and space-time was created at one point, and it was 30.7 billion years before now. And the universe when it was created was very small, it expanded, and gradually the matter started accreting, and then you got galaxies and stars. So most of the galaxies that you see here are born billions or billion years ago, and then they are formed in the place, and the whole thing is very. So this is the standard picture of the universe. And then we have the proof of the fact that there was a big bang, there was a dense phase of the universe. You see that in the dense phase of the universe, matter and radiation are very important and they are interacting. Right, so then as the universe expands, the density of matter reduces, and so the interaction stops at some point. And after that, the radiation keeps expanding and increasing. And in 1965, single book unexpectedly discovered this radiation. And now, at that time, there was no nuclear one radiation, but now there are many different observatories, and there is many plans, for example, in Pune, and what you get is a beautiful look at the radiation has got the form of a very beautiful black body. You know what a black body is? It's a equilibrium, and then it has got a temperature of 2.7 Kelvin. That is a very, very low temperature, but it is a proof of the fact that the universe was created in a very hot phase. Right, so now there is a complete alternative view of it. And this alternative view is that you are propounded by three people. And these three people are all extremely well known astrophysicists. There is Fred Hoyle, I want to show you. And this is from Body. And this is from Gold. So I've had the privilege of meeting all of you. But I met them in this photograph going up. It was in the 1950s. I met them in 1970s and 1980s. So you can see this photograph. So I told you that just like your university started with a shed, our center also started with a shed. And you can see the shed here, and that's called, they're called it ODP. And then it is one of the bonds. And you can see on the bottom here, there will be two different lines. This is Naresh and this is Pune. Body. That's me. Right. So now, so you see, these three people had a completely different theory of the universe. I told you that the universe is homogeneous and the universe is isotropic. But then they made one additional assumption, is that the universe must be the same at all times. So it is not only homogeneous and isotropic, but it doesn't change. So whether you look at the universe now, or whether you look at it many billion years ago, and or many billion years later, it will appear to be the same. Now how is it possible? So what is the difficulty? We know that the universe is expanding. So if the number of what the Big Bang say that it was a very hot phase started expanding in 1,000 planets. And then the density of the universe will decrease. But I am saying it's not right. What we hold on Hoyle said that the universe remains the same. So how do you manage it? You manage that by creating matter at a very slow, it is extremely slow rate. Create matter at a eventually form galaxies. So as the universe expands and becomes less dense, more galaxies will be, so the density will be. But it also means that there is no Big Bang. And there is no Big Bang, then how do you explain the radiation that you observe? So when the radiation was first discovered in 1965, Hoyle and Narlikar came out with very different ideas. And then there was also Vikram Singh, originally from Sri Lanka, who is also a astrophysicist in Wales. And then they had many theories about how to create, but now those theories are dependent on what happens at the ideas from. So there is a different solution. But the case for the steady state universe is not unique. I mean, not as complex. Right? So now, so you see that there are a lot of physicists who do not like the steady state theory. In the beginning, the steady state theory was very well received, but they did not like it as always a difficulty there. And one particular person who really did not like it at all was Martin Ryan. So he was, Hoyle worked in an institute called the Institute of Astronomy. Institute of Theoretical Astronomy. Now it's called the Institute of Astronomy in Cambridge. If you come to Pune, if you come to IUCAA, working there, so you will be there in the future. You will find that on one side of the road, we have got IUCAA, and the other side of the road, we have got the National Center for Radioactive Sciences, who run the GMR telescope, Professor Jayant Vishnu Narlikar. And similarly, in Delhi, we have got on one side, we have got the Institute for Astronomy, and then on the other side, we have got the Cambridge Laboratory. Cambridge Laboratory is one where all the great discoveries of nuclear physics were there, but in our time, the very famous was radio astronomy. And Martin Guy, so he was the main astronomer there, and we had this ability to bring a large number of things. In some of these guys, see a picture of the GMR in the antennas are similar, but they are very pioneering. Okay, meaning that this kind of thing was made for absolutely the first time in radio. And they counted the number of radio sources that we see in the sky. And you can argue that these radio sources were extragalactic. Because you can imagine that when the radio telescopes are, radio sources are discovered, you don't know whether they are in our galaxy or close to our galaxy or are they really smaller. So it was believed that they were all cosmology. And the question was, how are they distributed? So if the steady state theory is right, then these radio sources must be distributed uniformly. Whereas Martin Guy believed that they were not distributed uniformly, that the number increases as you go into parts. Because when you go to the distance, you are looking at the universe increasing parts. So there was a big argument between Hoyle and Rai about it. Because Hoyle was representing the steady state theory. And at that time, Narlikar was only about 21, 22 years old, like a young PhD student. What happened was that they were going to be a meeting like this in the Royal Astronomical Society in London. And Hoyle decided that he was making a presentation there, that he and Narlikar worked for a month to try to show that the observations are consistent with the steady state theory. But when the meeting started, and when the meeting took place, Hoyle couldn't go to the meeting for some reason. I don't know whether he did not know that deliberate. But then he said that he was only 52 years old. And Hoyle was already very famous and very angry, very senior astronomer. And so Jayant Narlikar made a presentation, and everybody liked it very much. And they believed that there was a lot of truth in what he was saying. And he instantly came to this. Because meaning that they got to, everybody realized in the Royal Society that here is a very young character. Like they were going to become famous later. So then, so this was a distribution of public sources. I have already told you about the personal microbackground. So before I come to that, then let me also, so there was another thing that they worked on, Hoyle and Narlikar, which actually again came very famous in India, and which is called the Calculated gravitation. You have got Newton's theory of gravitation, and after that you have got Einstein's theory of gravitation. The rest will be talking about Einstein, that kind of gravitation we will talk soon. And then, but there are certain problems with Einstein's theory. And so Hoyle and Narlikar made a new theory. It was called a conformally related theory. Meaning that in addition to the general relativity part, general relativity says that you can use any frame of reference to your things and it's the same. But Hoyle and Narlikar came out with a conformally related theory. Meaning that whether a body is small or a body is large, because it's small or because it's large, whatever its scale, the physics must remain the same. And through that theory, they explained various things which they believed were not explained in the Einstein's theory. So at that time, this was in 1964, 63, 64, 65. And in 1965, Jayant Narlikar came to India. And at that time, he was 27 years old. And he had become internationally known. So he went all over the country and gave talks. And because of his very soft and gentle nature and his ability to very easily explain the most difficult ideas, and the ability to establish a rapport with his audience, he became extremely famous as a communicator. And then he went under the Prime Minister, he went under the President. Radhakrishnan was the President at the time, and then everybody was awarded Padma Bhushan. They were probably one of the youngest ever award. I don't know whether anybody younger has got this. So now, he so I the in 1993 in December 1995 Paul and Burkish were other and they came out with a new theory for politics. So because I told you that the problem with steady state theory is that you can't explain the specific microwave. In the quasi steady state theory, the universe alternately expands and contracts and it becomes smaller. And because of various physical processes which take place, it is possible to explain the existence of the cosmic microwave pattern. All this completely different area than people work on. I only mentioned introducing it to you. So here the idea is the following, and so again Paul's idea, which said that where did life on Earth originate? So you know that life on Earth originated. There are theories which say that that will happen on the Earth itself. Because there really is no proof that there is life anywhere also. But you look at we are really now beginning to find thousands and tens of thousands of planets outside the solar system. Many of the planets are Earth-like. And then they are, therefore the Earth-like, they are at the same distance from the star as the Earth, or the star will be brighter and a little bit further away. So they are called terrestrial planets. Okay, which means that the conditions on them are the same resolution as the Earth, and therefore the chance that they will be light. And how many planets are there like this? I will tell you 10 to 11 galaxies which we can see with our vision. So 10 to 11, 10 to the 12 planets. There are so many planets, and in fact, basically imagine that people light those. There are probably life on Mars. Recently NASA and TV came out. And then probably life on moons of Saturn. So there is no problem. But at that time, in the 1960s, Paul said that life could have come to the Earth from a comet. So there are debris from comets which come and said that there could be life on them, primitive life, which is sprinkled on our atmosphere and then it comes to the surface of the Earth. It was a very radical theory. He could not publish it. Because he was such a famous physicist, he could not publish that theory. So Hoy, what he did was that he wrote a book called The Black Cloud. It was a science fiction story which mentioned this. And then the interesting thing is that many of the things he has said at that time are now about government. So what is the theory here? Is that you have got interstellar gas containing fire but then with rotational stars, then amplification of the bacteria, direct formation, biomaterial and again. So there are interstellar things that are happening. There are meteorites, there are comets which are coming in, light comes with them. So Narlikar proposed an experiment, and this is a book that So Narlikar proposed an experiment by which you send a rocket, a balloon, which are instruments, and then you look at the air, which is the atmosphere, which is very high up, look at is there any life there, and compare that to what you have there. So they actually carried out a bubble flight like that, and then because it was inconclusive. Other flight that you wanted did not happen. Maybe in the future, something can happen. So now, when in 1972, Narlikar left and came to the Department. As you know, it's a very famous, very beautiful institute right at the university. And there was an astrophysics group there, and he joined that group. And in the same year, I also joined the IUCAA, I was a graduate student. I also worked with him. After a year or two, he said, yes, I will do that, and then I became his student. So Narlikar produced very good students at that time, and who later on have all become leaders in their own fields, completely great fields. He was a very easy person to work with. And then he guided to the psychology. In the future, he asked me to work on a problem and I did pursue like it. It went on like that. So then, if you are an independent student, then instead of the human purpose. If you are less independent and you want to help, you do that. So he was extremely accommodating and understanding right there. And before he cleared for 1970 to 1979, when he moved to Pune to start his schools, IUCAA. And so he and I, that was already in the university for the Department of Mathematics there. And then we, two of us moved from Mumbai to Pune. And on the 1st June 1989, and there was nothing. When you see IUCAA now, it all looks very gorgeous. But at that time, it used to be a Buffalo official Buffalo because it belonged to the agricultural college. And then we made institute in the house and so on. So you can see it became very beautiful. And, so we had got, how many of you have been to IUCAA? Yes. So let us follow up always work there about that. And because we have scholars who can easily go there, and there are lots of events, so I urge all of you to go there whenever possible. And this is a football pendulum, which I want to do a pendulum. I saw inaugurated. You can see this particular ball, which is a very large pendulum. And by looking at that pendulum, the plane of the pendulum keeps rotating as the earth rotates. And that is a proof of the rotation of the earth. And just imagine that there were clouds in the sky like there are now. You could see the stars, you could see the sun and the moon. You wouldn't know that the earth was rotating. But if you look at it, if you pick up the pendulum and look at it, then somebody will theory to say that the earth is rotating. And the proof will come when the clouds clear. Here, Professor Narlikar and Professor Subramanian Chandrasekhar, and Charles Korea was a very well-known. It was, and then the Babuai Hamdar was one of the great classical news writers. So there is statue there. This is Aryabhatta. There. Newton, and this is the Newton's tree, which was bought from the council in which the uncle was dead. It was very fond of this 40 and it brought the trees. And you see that there is a lot of imaginative things that are gone into making the village. And this is a picture of the night sky. The picture I showed you some time ago was a deep view of that. This is like a normal night sky. Where the stars, and the architect's idea was that you should see such a night sky during the day. And how do you manage that? You see here that there is this small road, a small road line, and it is taken back on the inside. And there are Professor Rana at that time. You go over there and what he did was that the day on which the foundation stone of IUCAA was laid, so the sky on that day was very simple. Neither to make poles. And then during the daytime, light passes through the poles and you feel that you are seeing the night sky. And it is unbelievable. You go there and it's afternoon when it takes the night sky. So there are a lot of these kind of ideas there. Traditional and modern, you see that very traditional kind of steps with the black hole in the center. And then these two trees, you see there are stars and you calculate the gravitational field around. And then these are the most scores. So that will be very exact.
I was asking you, the trees were already there in the IUCAA or it was later?
Which one?
The two trees.
Now you see,
They were already there. They were constructed around there.
you see the story is like this. There were in that place where the buffaloes in the place, there were about 50 banyan trees. And we transplanted all of them. but we forgot to literally forgot to transplant it. Okay, so when the building was the food was ready, the architecture we can't have it. I said no cutting buildings. So we are standing there and talking, and then he said, okay, give me a night. So I got the idea that people are stars and cover the guidance in field, and we should create as a Lagrangian points and so on, everything we do. Okay, so you can see the binary system. But here you can see fractal patterns. Okay, then now you will normally go to building, because this is what you do. And what is relevant to you? There is a great deal of research which goes on, but what is really relevant to you is the IUCAA programs and universities. Now, I tried to get some pictures of the distribution of what happens. They are not very scientific pictures, but the number of associates. Some people like Professor Kembhavi, associates, they are not very associates of IUCAA. They are associated with well, within from the state for 3 months, 4 months, they use all the IUCAA facilities, and you can use the IUCAA list, everything. And you can bring us to students there. So I remember at time we had about 10 associates, but now we have got close to 270 associates. Then they are spread all over the country. This is not very clear, I don't know anything here. If you see, particularly the Northeast, they are our program is not an associate program in Northeast, I didn't care. The exact opposite. There are different parts of the country. So there are, you see that we have a Nema. There are about 70, 80 people attending. So imagine having a Nema like that 30 years ago. It would have been 24 people attending. Well, so the growth of astronomy is pretty spectacular. And then IUCAA, like this is the IUCAA program, so like that IUCAA all over the country. And we have a very large number of students. And then you see that maybe we get about 1,000 visitors or 1,500 visitors per year. You can't read it from there. The associates are 70%, but visiting students are 21%. Okay, so hundreds of students come there every year for doing the research, for attending events, etc. Then this is a picture of this is Fred Boy here, and this is student here in Malika. And then these are all Malika students, and we are best students. So this is also a very early picture, and it was taken just after I saw the tree, and you can now it will be very more recent. Then this is Malika teaching, to continue teaching here, and you see a picture which I showed you in Banaras, and then 13 years old, so there's not much of a difference. The way to teach it and the way to be done. Then these are his books. He wrote lots of books, some very technical ones, and then this is a remarkable tourism book. And if they get hold of it, this is great to the side of that. And these are books which I have co-authored with him. This is on Vedas, and this is the Jayant and Narlikar myself into the Marathi of stars. And here are these, you can see here science fiction. And you are a great public communicator, you know, and you should interact with the young students very well and teach them. And that was a big part of his life. And you see that we have the open houses on Science Day, and we do lectures and we have question answer sessions. And that was a very big part of the personality. And then the Naresh Dadhich and Prof. And his 81st birthday, somebody made this cartoon. And in Pune, on the walls of the city, people take paintings. They will prevent people from misusing the walls, and then they make paintings over all the mistakes in Pune, and there was people in Pune. And here you can see his painting. And then when he passed away, the Saka morning, Bengali also is the Saka. So this is that goodbye, sir, we will always remember that we will see. Thank you.
Thank you, sir, for such a wonderful lecture. I request the participants to interact with sir if they have any query. So sir is here for the next 2 days, including today. So you all are welcome to interact with him, even informally. Thank you, sir.
Do I need it? Am I audible without mic? Little bit without. So, Ajit has already said all nice things. So, what do I say? So, let me say that most about Narlikar, much has been written, he himself has written about himself, and got a biography himself. And much is written about IUCAA and but there is something about which not much is written, or at least to the audience like you. One should ask, what is the great, the most important science he did? And there I should say, he was always interested in the very fundamental questions. So if you ask the fundamental profound questions, have a long, long life. This question is very fundamental and profound. That cannot be answered very easily. And so people who work on those fundamental questions have to be very patient. That you attempt to do something, but not that you get to the answer. But I think the greatness of these people lies in the fact that they were trying to solve something so basic. Now, among these important questions, there are two questions which stand out. And any physicist cannot resist to work on them, or at least, or spend time about thinking about them. And one principle goes by the name Marx principle. Now, Marx principle is an enigma for all theoretical physicists. Everybody tries to work on it, try to understand it, but nobody has so far been able to grasp it. But but yet nobody can leave it. The reason for that is, so first you will ask what is principle. The problem is of its statement. Its statement is more philosophical and poetic. So the first problem is how to extract from the Max principle a scientific formulation. That you should be able to formulate in a quantitative manner, and then you try to solve it. So that's why it means different things to different people, and the simplest way of formulating it or statement is that everything in the universe exists because of its interaction with the rest of the universe. The thing here exists, or say I exist because of the interaction with all other things in the universe. This is how to say that every particle exists because of its interaction with them. Now here, when we say interaction, Marx does not specify what interaction. It's electromagnetic, it's gravity or what. The only thing which you will say, since this interaction is universal, that should be some force, some interaction in which all particles participate. And if that is the case, then we know from the Einstein's theory of gravity that the force in which all particles participate is the Einstein gravity. That is, anything that physically exists is linked to the gravitational Einstein's gravity. So you can ask then that interaction has to be gravitational interaction. Because that is the one interaction which is universally shared by all that physically exists. Einstein himself was also greatly enamored by Marx's principle. And he really wanted to incorporate in his general relativity, which he does to some extent. That is to say that the matter in the universe comes the space-time. So there is a strong relationship between the geometry of the space-time and the matter. But it does not really able to formulate an interaction between, to say that the existence of a particle is the sum of its interaction with the rest of the particles. So in other way we say the inertia of a particle is determined by its interaction with the whole other particles in the universe. So this was the question. I think nobody was able to formulate this in a clear cut. On that ground, now in this background, we have to view what Narlikar attempted. It referred to as conformal theory of gravity, or which was actually initially it was also called the new theory of gravity. There was in which, so they started with this, that formulating the max principle in a quantitative manner. What that means, that inertia of the particle, mass of the particle, you write as the sum of its interaction with all other particles. You write the sum and integrate it over, and it's a very sophisticated mathematics you have to use using the Green's terminology. But they were successful in formulating and incorporating the Marx principle. And the theory it gave rise to is what you are the new theory of gravity, the Hoyle-Narlikar. So they go by the name Hoyle-Narlikar theory, which has this beautiful part of conformal invariance. What it meant was, in very simple terms, that you have a physical laws. Now, all your fundamental units of the say length, time, and mass, all of them are uniformly are raised by a constant. That is what you say, a fundamental mass was say 1 gram, you say no, fundamental mass is 10 gram. Similarly for the time. And it stands to reason that what would you like to have in that case, that if there is a universal scaling of all the physical constants, the physics should not change. Because it does not matter whether it was the unit was 1 or it is whatever you call it is 10. However, you know that Einstein gravity is not conformally. All other physics is. Electrodynamics conformally invariant, and then your nuclear physics. Other than the gravity, all things are conformally invariant. But gravity is not. And the reason for that is, so when we are doing this, asking for the conformal invariance, all other theories you have, where the space-time is given to you, fixed, in which you prescribe the physical laws, like Coulomb's law or the Newton's gravity or gravitational law. So there, the space-time does not involve, is not involved. And then you make a same universal scaling, things should remain the same. But in the case of gravity, gravity cannot be described independent of space-time. There, the gravity is described by the curvature of space-time. So space-time itself is dynamic. And that thing is space. So that the space-time is not conformally invariant. You cannot keep that conformally invariant as you scale it. As you scale so that is why that is breaking. Then the Hoyle-Narlikar theory, they have to add something to this, to Einstein's lecture, to make this conformally invariant. But that point, the important thing was that this addition, what the modification they did, was governed by the fact of incorporation of Marx principle. So it is the Marx principle's incorporation that led to that modification, which resulted in making gravity conformally invariant. have this. So which was better? So that this is the 1963 or 64. This new theory of gravity papers were published. Overnight, oil was already known, but Narlikar became a household name. It was something, because the theory was really incorporating something which has defied all the efforts of the people so long in Christendom. But unfortunately for that, the cosmology it accords to, cosmology gives rise to, is a steady state. What Ajit has already said, and the steady state theory is aesthetically very beautiful, but it has a physically very undesirable feature. Aesthetically, it's beautiful. This is the universe remains the same, both in space and time at all times. It's a steady state that you have, so which has no end, no beginning. So the universe comes into existence as it is. And of course, now you say the universe is expanding. This is an observation. So when the universe is expanding, then how do we retain the matter density same at all times? Because the way the galaxies are going apart, so there is some empty space being created. So that will, their density will be different. To keep the density separate, that there should be a continual new creation of matter. And but that is where the new creation, this is the matter coming out of nothing. So that violates our celebrated conservation. And in physics, all conservation principles are very sacred, but more so the energy conservation. So that's what that we said, that this is all fine, but how do we avoid it? Energy conservation. And that too. But then to this one very cavalier answer that already gave, one that, well, you accept that you also violate this at the Big Bang. When the universe is created at the Big Bang with the big explosion, there also the matter is created by out of nothing. So but then they said that is true, but you see, at one time you can try to digest something so uncomfortable, but you are thinking all the time. So to that phrase, you was that right, this is true, but by bringing it that happens all the time, what it is you are bringing it that we should be able to probe this deeper, that it is happening. You see that going to Big Bang, where you have the densities go to infinity and this, that is the sort of an event which is not accessible to India. However, it's being created all the time. So that event is something, this is some process which should be accessible to deeper experiments and observations. So it's going to work that if we accept this, this will motivate us to probe this, whether it is true or wrong. However, this 1963 cosmic microwave background radiation result totally established the Big Bang. That the universe was created in the Big Bang, and we could build the entire history of evolution consistently. So that all the scientific opinion certainly will be Big howsoever attractive your steady state theory in principle may be. So that's the one we will have. And then of course, these three gentlemen, the creators of steady state theory, the Tommy Gold, Herman Bondi, and Fred Hoyle. So Herman Bondi was the first to give up. He said, look, statistic theory was a brilliant and very novel new idea. It is too bad that experiments don't agree. And we can't do anything experiments don't agree. It's more or less the same thing with the Tommy Gold. Fred was the one who did not want to give up. And that's when he came about this very ingenious, though a very labored idea. The idea of he had was, it asking him the question was this, that can I not create the CNBR like radiation without a Big Bang? And so he said, okay, look here, steady state theory, it is could be in cycles, so where there always be a matter dust present. And then you could see the matter dust in terms of a what? Your iron thin iron needles. And that thin iron needle can ionize the starlight which you feel, and can give you exactly the same effect as the your cosmic microwave. So it was ingenious, and this approach is that this kind of thing with the metal needles with the radiation, polarization. This has been done in, you can do it in level. So you can do an experiment. But this is a labored thing that such a thing happens here. In the case of a Big Bang, it is a natural accumulation. But even if it's a labor, it was very ingenious. That labor I put what is steady state. So which we say that the universe is in many cycles, and each has many Big Bangs. And so that's overall it is in steady state. This steady state of long periods. So you can say that the one cycle is how many billion years old. So in that cycle it would be like Big Bang and overall. So that was a very ingenious one. When Jayant joined Hoyle as a PhD student, so Hoyle gave him a list of the problems he can choose from. Among them, there are gravitational radiation nowadays. But steady state theory was not. So Jayant asked him, why not steady state theory? He said, no, I don't want to deal with it. The steady state theory is a controversial theory, which is all right for an old man like me to work on. Because I can withstand that to this criticism. But I don't want a young man to get into it. but the student was around as teacher. So where does he joins in is where you see the challenges posed by the cosmic microwave radiation to steady state theory. Then you say, if you assume that whatever you do for the Big Bang theory, how can you not do this? So for example, they were the first to say, study or predict the formation of supermassive black holes in the galaxies. But for that they had their theories, negative energies, what we call C field. However, they were the first, but you see, soon afterwards, Martin Rees and Donald Lindenberg, they also came to the same conclusion using the conventional Big Bang theory. So here now you have a situation that something which you do, which is unusual, which is novel and very imaginative, very creative, but ultimate test of the thing is observation and experiment. Experiments don't favor your theory. Then your theory does not get it. That was the one question. Another important question, but on the same when we are saying this, we must say that these questions were profound, and these were the questions which were really the leading scientists of the day were all very involved in this. So the question about the profundity of the question is two parameters. One, its own intrinsic profundity, the kind of question we are asking. Second thing is how that question is viewed as a profound by the scientific community. And on both counts, that the question is the new theory of reality addressed was one of the most important questions. So, but it did not get a currency simply because the cosmology gave rise to did not have a observation. Another similar, very fundamental question is the era of time. So, as Ajit has pointed out to this, the whole physics is time symmetric. But we only adopt the solution, the retarded solution. Advanced solution is equally valid so far as the mathematics equation is concerned. The question is, so here of course you could take that most of us or most of textbook take the pragmatic view that we choose the target one because that is what agrees with the experiment. I don't see advanced reaction. So I throw it out. But if you are really interested in really the deep fundamental question, then I ought to see that my equation gives both the solutions. They are equally valid, then there should be some reason about the other solutions I don't observe, while I don't observe. So this is a fundamental question. So that is what we do that. So here we choose the era of time as a choice. We describe The moment we take the only accept the retarded solution, that means I have chosen the error of time. So this question was for the first time was addressed by Richard Feynman and John Wheeler in 1945, and goes by the name Wheeler-Feynman observer theory. So there, that's where the first time in the fundamental physics there was a question of the possible decay. The rest of the universe came. And their answer was this, that the advanced solution or advanced reaction is, if you consider the thermodynamics of the universe as a whole, then the advanced reaction is absorbed by the rest of the universe. And what you observe is only that your the target. And this theory, this was reformulation of the say electrodynamics in something called the accelerated. So you have now the two formulations of electrodynamics or available for any field. One is where you assume that you have some charge distribution which creates a field around it. And that field is at every point is uniquely defined. So that is a singular way of doing it. So if you want to do the experiment, that is how we do it. However, in this we always say we assume an error of time that we only accept that retarded. The other thing that we Feynman Wheeler formulated the accelerated distance. When you have a charge, then some excel, the photon goes and it interacts with the other charge, and you compute this. And in this, then you have both advanced and retarded thing. So what happens to the advanced part? That is where the problem is that it's absorption of the advanced reaction by the rest of the universe. But later on, the accelerated distance was very nice, very well appreciated, but it had no practical use because it was very difficult to work. So it's not only that engineers who are fond of simple ways of doing, you not give them, they want a formula and how to apply it to electricity. At some level, we in theoretical physics too also we want to do calculation ease or conceptual ease. So that's all that we did. And the propagators both, Feynman and Wheeler, they also gave it up. Actually, Feynman told Naresh Dadhich, they were presenting their theory of the extended distance theory. And then, Feynman, he said, but you will not be able to quantize it. And he said, he himself had worked very hard and could not get it quantized, and that's why he gave up. So, Wheeler, when they talk, one of the most intellectually brilliant and more satisfying. This is not Jayant's his own thing. You as a lobby, listen to you that he admits this, that intellectually most satisfying to their formulation of external distance created by in curve space. So that means they had done the Royal Narlikar they did for the flat version because it's based on external distance formulation of created by and Royal Narlikar they did it in the curve space. So this was very significant. And this is what they presented to Feynman. And Feynman said, yeah, I agree with his mind. But he said, you will not be able to quantize it. And he said, he gave it up because then they saw that the electrical challenge, and then they found something interesting here, that they were able to quantize it, but in their formulation of this, so when you quantize, you have this renormalization, where all your infinity, your throughout, which we don't know in itself. One of the most repulsive part of the field theory is the process or the concept of renormalizations where we throw out the infinities without any physical justification. The only justification ultimately remains is that after throwing it out base, what we predict it agrees with the experiment. So it's essentially, again, is a more effective way. That this is which is entirely driven by phenomenon. It's a phenomenon which experimental should be some for that to have this solution. But I don't understand, nobody understands. And second, another way of this thing, that you have the integrals which becomes divergent and then you cut off. In Boyle-Narlikar's theory, the theory has a natural cut off and there is no renormalization. So simply on this count, this would have been one of the outstanding theory. That where you are able to get rid of renormalization in the quantizing that. However, this again did not get a currency simply because so there the question was that your advanced reaction which you have here, for that they require the response from the rest of the universe. And that response to the rest of the universe, the cosmology required us this. The universe is in steady state, then this will be. So again a very brilliant work, which is Nobel Prize is what I don't always consider Nobel Prize is the only the most measure of profoundness of theory of profoundness of result. But this particular piece, both these particular pieces were really of that class. There is no doubt about it. But again, because they were They were anchored in the steady state cosmology. Again, they didn't get currency. So I would end it by saying this, that what gets currency actually depends upon a couple of factors. One is, sometimes it might happen that you do something very brilliant, very creative, outstanding, but the idea is ahead of its time. So I'm just trying to put that support both these ideas of the conformal invariant gravity theory or new theory of gravity and the extent at a distance formulation of Narlikar in short space time. If you have suppose these things were done in say 1940, then also you say they will be thrown at the head of the time. But even if you have reading things much ahead of time, might not get immediate experimental support, but so long as there is no contradiction by the experiment, the idea will stand. So if you see if that is the case, and then suppose 1960s your income, that is still no. So there are like many ideas, even similar things like you said, like the C field with the negative and the field. Today, we have inflation. Again, the same story, we don't know what it is. Then you have to do dark energy loaders in the phantom field, which are even worse than the C field. So, but since phenomenology admits that kind of a thing, so I would say that the unfortunate thing for these two brilliant ideas, things, was that it did not have really enough time for people to appreciate and become popular because the observation was right there. So, but I would say in the sake of the genuineness of the science itself, it isn't being addressed. And sometimes we should be able to keep the observation and experiment, which is the ultimate stage. I'm not denying this, but you appreciate the strength and the profundity of the principle for the world. I think that is what right. If I take that into these two pieces of work, really sign about for the next. Thank you.
Thank you, sir, for such an informative presentation. I will now request the participants to put forward their queries, if any.
Thank you, sir.
So since there is no query, I would once again like to express our gratitude towards you, sir. Thank you very much.
Can I ask a question?
Yes, yes, sir.
Yes, yes.
I missed out what you were speaking, I don't know. So I'm asking it to you, this, about the thermodynamical arrow of time.
Yes.
When we say the entropy of the system. It increases. But as observed by whom? Is the entropy observer dependent or it is observer independent function?
So entropy observer dependent. So one thing is, so when you are having this expanding universe is expanding. So when you are doing this, there we have already given some bit of relativity. That where I choose a specific direction to time and the space. So there is this, I do a space-time split. It's the three persons time. So when we are talking about the invariance is not in the usual four-dimensional space-time, but with this space. Now since the arrow of time I already have fixed. So then that entropy being independent is only respect to the spatial part. And for all the observers, that should be this. So here, and then we say that entropy, but in this, entropy increase or what here the question here we are asking was from the basic physics to construct the arrow of time. But in all these physical phenomena which we associate with the time progression, whether it's entropy or the expansion of the universe or the leaking out of the radiation to the black hole, this is only an association. Nobody sees us. But here was more fundamental question that I start by basic electrodynamics or basic theory of gravity that you have, and there I see how the advanced reaction is not observed. How the advanced reaction is absorbed in the Miller-Feynman theory by the rest of the universe, and how the advanced reaction is absorbed by the interaction, cosmological interaction, the interaction of the rest of the universe. So that's the.
I mean, I have Gibbs paradox in mind and some amount of observers go in the phenomenon.
Cosmos, then you can, point is, that you don't have, where you do not have a space-time split. In cosmology, I always do the cosmology in the small depth.
Thank you, sir. So we have a slight change in the schedule for the events of the day. After the talks delivered by our esteemed speakers, instead of moving in modern physics to be delivered by Professor Ajit Kembhavi, after which we will proceed for the lunch break, followed by the oral session.